What if every moment of existence, every breath, every star's birth, even the universe itself, was trapped in an endless cycle, repeating over and over like a cosmic record stuck on replay? The idea of time loops isn't just science fiction. It's a haunting possibility that some of the brightest minds in physics and cosmology are taking seriously. Imagine a reality where the Big Bang wasn't a one-time event, but merely the latest iteration of an eternal reboot, a universe caught in a loop so vast, so incomprehensible, that our entire history might just be a fleeting fragment in an infinite sequence. This isn't just about déjà vu or eerie coincidences. We're talking about theories that rewrite the very fabric of time, space, and existence. Today, we're diving into 30 of the most astonishing theories about the universe's first time loops, ideas that blur the line between science and philosophy, between what we know and what we can barely fathom. Some of these theories suggest that time itself could be circular, with the end of one universe birthing the next in an unbreakable chain. Others propose that black holes might be cosmic reset buttons, warping reality into repeating patterns. And then there are the mind-bending ideas that our entire universe is just one layer in a stacked reality, where time loops like a Möbius strip, folding back on itself in ways we can't yet perceive. These aren't just wild guesses, they're hypotheses backed by equations, observations, and the kind of bold thinking that pushes human understanding to its limits. Why does this matter? Because if even one of these theories holds a shred of truth, it changes everything: our place in the cosmos, the nature of free will, even the meaning of existence. Think about it. If time is looping, are we truly making choices, or are we just living out a script written by the universe's own repetition? Could the answers to life's biggest questions be hidden in the echoes of past cycles? Strap in, because we're about to embark on a journey through the most provocative, spine-tingling ideas in modern physics, theories that don't just challenge what we know but invite us to wonder what else might be waiting, undiscovered, in the loops of time. The first theory takes us straight to the heart of cosmology's biggest question. What if the Big Bang wasn't the beginning but a cosmic reset? Picture this. Instead of a single explosive origin, our universe might be stuck in an endless cycle of death and rebirth, like a phoenix perpetually rising from its own ashes. This idea, known as conformal cyclic cosmology, was pioneered by physicist Roger Penrose, who suggests that the universe doesn't just end with a whimper or a bang, it loops. As one universe fades into an era of endless expansion, where particles lose energy and time itself becomes meaningless, quantum fluctuations could trigger a reboot. Space-time crumples, laws of physics reset, and suddenly, what looks like the end becomes the seed for a new Big Bang. But how could something so vast, so seemingly irreversible, just start over? Penrose points to entropy, the universe's tendency toward chaos. Normally, entropy only increases, but in this model, when the universe stretches into an ultra-smooth, featureless void, entropy effectively resets to zero. It's like erasing a chalkboard so completely that even the dust vanishes. At that point, the distinction between the end of one cycle and the start of the next blurs. The fading embers of the previous universe could create ripples in space-time, imprinting faint echoes of the past onto the newborn cosmos. In fact, Penrose claims to have found these echoes in cosmic microwave background radiation patterns that might be scars from universes long gone. This isn't just poetic speculation. The math behind it is grounded in Einstein's general relativity and quantum mechanics, yet it challenges our deepest assumptions. If the universe loops, does that mean every star, every civilization, every moment repeats eternally? Or could each cycle spawn subtle variations like a cosmic remix of reality? The implications are dizzying, whether we're trapped in an infinite rerun or part of an ever-evolving sequence. The idea forces us to rethink not just our past but our future. And if Penrose is right, the evidence might already be written in the sky, waiting for us to decode it. Now imagine a universe where every detail, every thought, every star, every breath you've ever taken repeats itself precisely, endlessly, in an infinite loop with no variation whatsoever. This is the chilling premise of the eternal return, a concept philosopher Friedrich Nietzsche proposed not as scientific theory, but as a thought experiment to test how we value existence. But what if Nietzsche's poetic musing wasn't just metaphor? Modern cosmology has dragged this idea from philosophy into physics, suggesting that under the right conditions, the universe might not just loop, it could replay identically, like a film on permanent rewind. At first glance, the idea feels impossible. How could a universe as vast and chaotic as ours repeat down to the atomic level? The key lies in spacetime's geometry. If the universe is finite but unbounded like the surface of a balloon, expanding and contracting then given enough time, quantum states could reconfigure in the exact same sequence, like a cosmic deck of cards reshuffled into identical hands. Mathematically, in an infinite timeline with finite possible states, repetition isn't just likely, it's inevitable. Some interpretations of quantum mechanics even suggest that every possible outcome must eventually manifest, meaning your life, your choices, even this video would recur infinitely. But here's where it gets stranger. Physicists like Alexander Vilenkin argue that if the multiverse theory is correct, with countless universes bubbling into existence, some of them would inevitably share identical initial conditions. Like rolling dice forever, eventually you'll get the same number twice. Applied cosmologically, this could mean parallel universes trapped in synchronous loops, each one a mirror of the others. The eerie implication: if even one atom diverged at the Big Bang, our universe might now be wildly different. Yet if the cycle is absolute, that divergence could never happen, fate locked in place by the ironclad laws of repetition. Nietzsche's nightmare or revelation wasn't about physics but meaning. If everything repeats, does joy lose its savor or pain its sting? Modern science reframes the question: could the universe's architecture demand such repetition? The answer might hide in the fabric of spacetime itself, woven into equations we're only beginning to unravel. Whether poetic provocation or cosmic inevitability, the eternal return forces us to confront a haunting possibility that nothing is truly new and every moment is both first and forever. Black holes' cosmic voids so dense not even light can escape might be more than just destroyers of matter. What if each one is a cosmic womb, birthing entirely new universes with their own laws of physics? This mind-bending idea, known as black hole resurrection, suggests that every time a black hole forms, it doesn't just trap matter, it triggers the creation of a fresh universe inside it, hidden from our own. Physicist Lee Smolin took this even further with his theory of cosmological natural selection, proposing that black holes are the universe's way of reproducing, with each new cosmos inheriting tweaked physical constants from its parent. Think of it like a cosmic family tree. When a black hole collapses, the extreme conditions at its core, where gravity warps spacetime beyond recognition, could spark a new Big Bang. But here's the twist: the physics inside that newborn universe might differ slightly from ours, as if the cosmos is evolving through trial and error. Smolin argues that over countless iterations, universes better at producing black holes would outcompete others, leading to a multiverse fine-tuned for black hole creation. It's Darwinism on a galactic scale, where survival of the fittest applies to entire realities. The implications are staggering. If true, our universe could be one branch on an infinite fractal of nested realities, each birthed in the heart of a black hole from a parent universe. Time loops wouldn't just repeat, they'd branch, mutate, and multiply. And if black holes are cosmic seeds, then the supermassive ones at the centers of galaxies might be especially significant. Could Sagittarius A, the black hole at the Milky Way's core, be incubating an entire universe right now, completely unknowable to us. Critics point out the lack of direct evidence, but Smolens's idea offers a provocative answer to why our universe seems so finely tuned for life. Maybe the constants of nature, the speed of light, the strength of gravity aren't arbitrary. They could be the result of eons of cosmic selection, with black holes as the mechanism. Imagine a reality where every collapse is both an end and a beginning, where time loops aren't closed circles but spirals, endlessly branching into new possibilities. It's a vision of the cosmos that's as beautiful as it is unsettling, one where destruction and creation are two sides of the same coin. What if death isn't the end, but just a branching path where your consciousness leaps to the nearest version of reality where you're still alive? This unsettling idea, known as quantum immortality, takes Schrödinger's famous cat experiment to its ultimate extreme. Imagine the cat isn't just alive or dead in a box, it's both, existing in parallel realities until an observer peeks inside. Now replace the cat with you. Every moment you survive a near miss, a car swerving just in time, a missed step on the stairs, could be evidence of your consciousness hopping between timelines, leaving behind universes where things ended tragically. In this view, death isn't absolute. It's a filter your mind can't perceive, editing reality so you only experience timelines where you persist. The math behind this stems from the many worlds interpretation of quantum mechanics, where every possible outcome spawns a new universe. When Schrödinger's radioactive atom decays, or doesn't the universe splits, but here's the twist, your awareness follows the path where you continue existing. You'd never notice the branches where you died because your consciousness can't inhabit them. It's like flipping a coin infinitely. Heads you live, tails you die, but you only ever wake up in realities where the coin landed heads. Over eons, this could create a subjective time loop where you always find yourself alive, no matter how statistically improbable survival becomes. Critics argue this reduces consciousness to a cosmic glitch, a side effect of probability. But proponents like physicist Max Tegmark suggest that quantum immortality isn't about cheating death forever, but about the bizarre nature of observation. If consciousness requires a living observer, then from your perspective, you're always the observer who survives. The implications are staggering. Could aging itself be a slow-motion version of this? As your body fails, you'd unconsciously shift into realities where medical breakthroughs or flukes extend your life, creating a loop where death perpetually retreats over the horizon. Tie this back to time loops and the picture grows even stranger. If quantum immortality holds, your subjective timeline might feel linear, but in the multiverse, it's a fraying rope with countless dead-end branches snipped away. You're not looping through identical cycles, you're surfing an infinite wave of possibilities, bound only by the single rule that you must keep observing. Whether this offers solace or existential dread depends on perspective, but one thing's certain: the universe might be far weirder and far more personal than we ever imagined. What if the universe isn't truly three-dimensional, but a vast cosmic hologram, a shimmering projection of information etched onto a two-dimensional surface at the edge of reality? This isn't science fiction, it's the radical premise of the holographic principle, a theory that could rewrite our understanding of time loops entirely. Imagine the cosmos as a cosmic movie screen, where every event from the birth of stars to the flicker of your thoughts is just data encoded on a distant, flat boundary. And if that's true, then the universe might not just loop, it could reboot like a film reel spinning back to its first frame. The idea stems from the work of physicists like Leonard Susskind, who realized something astonishing. The information needed to describe everything inside a region of space, every particle, every force, could fit perfectly on its outer surface, like a holographic sticker containing an entire world. This isn't just a metaphor. In the math of string theory, there's a concrete example called AD S/CFT duality, which shows how a universe with gravity like ours can be perfectly mirrored by a quantum field theory operating on its boundary, no gravity required. It's as if the 3D world we experience is a shadow cast by a 2D code we can't see. Now apply this to time loops. If the universe is fundamentally information, then a reset wouldn't require collapsing stars or cosmic contractions, just a rewrite of the data. Picture a DVD playing the same movie on loop. The scenes don't physically repeat, the code just reloads. Similarly, a holographic universe might replay by reprojecting its encoded information, creating the illusion of cyclical time. Each loop could be a fresh rendering of the same underlying data, with subtle quantum tweaks introducing variation like a cosmic director's cut where the story stays the same, but the details shift. The implications are staggering. If the holographic principle holds, then time itself might be an emergent property, not a fundamental feature. Loops wouldn't be carved into space-time, they'd be baked into the universe's source code. Even black holes, often seen as cosmic dead ends, could be storing the blueprint for new universes on their event horizons, their surfaces acting as celestial hard drives waiting to reboot. And if Suskind's right, the evidence might lie in the way quantum information scrambles and reappears, like a cosmic save file waiting to be reloaded. This isn't just about physics, it's about the nature of reality. Are we living in a universe or a simulation, a projection or the thing itself? The holographic principle blurs those lines, suggesting that time loops might not be cycles in space, but resets in the deepest layer of existence. And if that's true, then every moment, every choice, every breath might not just repeat, it might be recalculated. Einstein's equations didn't just reshape gravity, they cracked open the door to time itself bending into loops. Hidden in the math of general relativity is a bizarre possibility, closed time-like curves or CTC, where space-time warps so severely that it circles back on itself like a twisted ribbon. Picture a path where, if you walked far enough in one direction, you'd eventually return to your starting moment, not just in space, but in time. This isn't fantasy, it's a direct consequence of the universe's geometry under extreme conditions. The first hint of this came from Kurt Gödel, the mathematician who proved some truths can never be calculated. In 1949, he stunned Einstein by showing that a rotating universe, one spinning like a cosmic top, would naturally twist spacetime into CTCs. In Gödel's model, the entire cosmos acts like a giant time machine. If you traveled far enough along the axis of rotation, you'd loop back to your own past. No paradoxes, no magic, just pure physics. Gödel's universe never matched our observations. We don't live in a spinning cosmos, but the message was clear. Einstein's laws allow time loops if reality cooperates. Wormholes take this idea even further. Imagine a tunnel stitching two distant points of spacetime together like a cosmic shortcut. If one end moves near a black hole or accelerates to near light speed, time dilation would twist the wormhole into a CTC. Enter one mouth in 2040, exit the other in 2020. Suddenly, you're shaking hands with your younger self. Physicist Kip Thorne famously explored this in the 80s, proving such wormholes could exist mathematically if stabilized by exotic matter with negative energy. The catch: negative energy is hypothetical and wormholes are wildly unstable, but the math holds. Time loops aren't ruled out by physics, just by practicality. Critics argue CTCs violate causality. What stops you from preventing your own birth? The answer might lie in quantum mechanics. Some models suggest paradoxes self-correct, like a river flowing around a rock, forcing events to stay consistent. Try to change the past, and the universe might adjust your actions to preserve the timeline. Others propose multiple worlds. Each loop branches into a new reality, sidestepping paradoxes entirely. The wildest implication: if CTCs exist, the universe might not just loop. It could be threaded with cycles we can't yet perceive. every black hole, every warp in space-time might hide fragments of time folding back on itself. We're left wondering, are we the first iteration or just one echo in an endless chain? The equations whisper yes, but the cosmos keeps its secrets for now. Here's the next segment of the video script, adhering to all your guidelines. What if everything you remember, every moment, every thought, even your sense of self, wasn't real, but just a random flicker in an endless void? This unsettling possibility lies at the heart of the Boltzmann brain paradox, a cosmic thought experiment that turns our understanding of time loops inside out. Imagine a universe that exists forever, drifting toward maximum entropy, a state of total chaos where matter and energy are evenly spread like steam fading into empty air. In such a universe, random quantum fluctuations could, by sheer chance, momentarily arrange particles into a self-aware mind, a lone consciousness with false memories of a past that never happened. That's a Boltzmann brain, a ghost in the cosmic machine, convinced it's lived a full life, only to dissolve back into the void moments later. The paradox emerges when we ask, which is more likely, that our structured, ordered universe is real, or that we're Boltzmann brains hallucinating it? Statistically, in an eternal cosmos, a single self-aware fluctuation is infinitely more probable than the evolution of galaxies, stars, and life. After all, assembling one conscious moment requires far less energy than crafting 14 billion years of history. If the universe truly lasts forever, these phantom minds would outnumber real observers like us by an unimaginable margin. So why don't we think we're one of them? Physicists recoil from this idea not just because it's eerie, but because it undermines science itself. If most observers are Boltzmann brains, then our data about the cosmos could be illusions. The Big Bang, the laws of physics, even your childhood memories might be elaborate fiction conjured by chaos. Some theorists, like Sean Carroll, argue this paradox isn't just philosophical, it's a crisis for cosmology. It suggests our universe can't be eternal and uniform, or Boltzmann brains would dominate reality. Instead, there must be a boundary, a cutoff point where time or entropy resets, preventing infinite fluctuations. This could imply a cyclical universe, a big crunch, or even a multiverse where pockets of order persist like islands in a sea of chaos. Critics counter that the paradox might reveal flaws in our statistical assumptions. Maybe consciousness can't emerge from random noise, or perhaps the universe isn't as eternal as we thought. Others propose an unsettling middle ground. What if time loops themselves are Boltzmann fluctuations? A lone brain might hallucinate not just a past, but a cyclic past, a false memory of universes rebooting endlessly. In this view, the very theories we've explored could be phantoms, products of a fleeting mind grasping for patterns in the dark. The chilling beauty of the Boltzmann brain paradox is that it can't be disproven. Every argument against it, every reference to evidence, logic, or physics, could itself be a hallucination. It's the ultimate skeptic's trap, a cosmic "how do you know?" that forces us to question not just reality, but our place in it. If Boltzmann brains are possible, then time loops might not be features of the universe, they could be glitches in the minds dreaming it. And that leaves us with one haunting question. If all of this is just a random flicker, does it matter that it feels so real? What if time loops aren't cosmic accidents but deliberate reboots, like a programmer hitting reset on a glitching simulation? This is the spine-tingling premise of the simulation hypothesis, where our universe isn't the base layer of reality but an artificial construct, and time loops could be nothing more than debug cycles or save file reloads. Philosopher Nick Bostrom laid the groundwork with his famous trilemma. At least one of these must be true. Either civilizations never reach the tech to simulate realities, they choose not to create them, or we're almost certainly living in one. If the third option holds, then glitches in our reality, déjà vu, déjà rêvé, even Mandela effects might not be quirks of memory but literal patches in the code. Think of it like a video game crashing. When a system overloads, developers roll back to an earlier save. Now imagine our universe as that game. A time loop wouldn't be a natural phenomenon but a forced reset, triggered when the simulation encounters unfixable errors. Maybe a paradox, a cosmic overflow, or even a player tweaking variables. The loop resets events to a stable point, letting the program rerun until it reaches a viable future. It's not science fiction. Silicon Valley elites pour millions into simulation research, and physicists like Seeler's Bean suggest we might find proof in energy limits like a pixelated grid hidden in cosmic rays. But here's where it gets eerie. If we're in a simulation, time loops could serve darker purposes. Imagine a civilization running ancestor simulations to study historical outcomes, replaying the 20th century with slight variations to test nuclear war scenarios or pandemics. Each loop might be a new iteration of the experiment, with humanity none the wiser. Glitches like déjà vu could be artifacts, echoes of past runs bleeding through. Even quantum indeterminacy fits this model. The simulation only renders precise outcomes when observed, conserving processing power. Bostrom's trilemma forces a brutal conclusion. Unless humanity is alone or uniquely ethical, the odds favor us being simulated. And if that's true, time loops aren't mysteries, they're features. A simulated cosmos wouldn't need cyclical universes or black hole resets. It could rewind with a keystroke. The question isn't whether we can escape the loop, but whether we're meant to notice it at all. After all, what player tells their characters they're in a game? The answer might lie in the glitches, not just in reality, but in us. If time loops exist, they might not be written in the stars, but in the code we're only beginning to suspect. Hidden in the faint afterglow of the Big Bang, there might be cosmic graffiti scars from a universe that existed before ours. The cosmic microwave background, or CMB, is more than just a snapshot of the infant cosmos. It's a fossilized record of the universe's earliest moments, imprinted with secrets that could rewrite history. But some of those secrets don't fit the standard story. Strange anomalies like the so-called axis of evil, a bizarre alignment of temperature fluctuations that defies randomness, hint at something deeper, something cyclical. What if these aren't just statistical flukes, but echoes of a previous cosmic cycle? Roger Penrose, the Nobel-winning physicist behind conformal cyclic cosmology, believes he's found smoking gun evidence in the CMB. His theory predicts that when one universe dies and another is born, black holes from the previous cycle leave faint, circular imprints in the radiation like bruises on spacetime. Penrose calls these Hawking points, named after Stephen Hawking's work on black hole evaporation. These aren't random hot or cold spots. They're concentric rings of temperature variation, as if the universe is whispering, "This has happened before." And if he's right, the CMB isn't just a baby picture of our cosmos, it's a palimpsest layered with the ghosts of past universes. Skeptics argue these patterns could be coincidences, cosmic static masquerading as meaning. But the math is provocative. In Penrose's model, when a universe reaches heat death spreading into an endless, featureless void, quantum effects cause spacetime to lose all sense of scale. At that moment, the infinite future of one cycle becomes the Big Bang of the next, resetting entropy to zero. The transition isn't violent, it's a graceful handoff, with black holes from the old universe leaving faint traces in the new one's CMB. Like a fingerprint on a pane of glass, these Hawking points would be subtle but unmistakable to those who know how to look. What makes this so compelling is that it's testable. Penrose and colleagues claim to have identified dozens of these anomalous rings in CMB data, each spanning billions of light years. If verified, they'd be the first physical evidence of a pre-Big Bang universe, a cosmic before lurking in the afterglow. The implications would be staggering. Our universe isn't just one iteration in a sequence, but a link in an infinite chain, each cycle inheriting faint relics of its ancestors. The axis of evil, then, might not be an error in the data, but a cosmic signpost pointing to the loop. Yet the debate rages on. Critics point out that the CMB is notoriously noisy, and finding patterns in randomness is a trap humans fall for constantly. But if even one Hawking point is real, it forces us to confront a humbling possibility. The universe might not have a beginning or an end, just phases in an eternal rhythm. And somewhere in that rhythm, our entire existence could be a single note echoing across time. Time doesn't just move forward, it might shatter, reverse, and reset itself in a cosmic game of rewinding entropy. One of the most radical challenges to our understanding of time loops comes from the idea that entropy, the universe's relentless march toward disorder, could flip directions in a hypothetical big crunch. Imagine a universe not expanding forever, but collapsing back into a singularity, dragging time itself backward like a film played in reverse. Stars would unburn, shattered glass would leap back into whole panes, and memories might unravel as entropy decreases, resetting the cosmic clock for another cycle. This isn't just fantasy, it's a contentious battleground in physics centered on a 19th century mathematical gem, the Poincaré recurrence theorem. Henri Poincaré proved that in a closed system with finite energy like, say, a universe, every possible configuration of particles must eventually repeat. Given enough time, the air molecules in your room could spontaneously arrange to one corner, or the entire cosmos could stumble back into a state indistinguishable from its starting conditions. The catch: for a universe as vast as ours, enough time could mean a number so large it defies comprehension, like waiting a Googleplex years for a deck of cards to shuffle back into perfect order. Yet the math holds. If the universe is finite, recurrence isn't just possible, it's inevitable. But here's where physicists clash. Some argue that entropy reversal in a big crunch could shortcut this process, forcing the universe into a reset without waiting eons. In this model, gravity, the great architect of cosmic structure, would eventually overpower expansion, pulling everything back into a fiery collapse. As matter condenses, entropy could decrease, like rewinding a shattered vase reforming from scattered shards. The universe would hit a singularity, not with a bang, but a rewind, birthing a new cycle from the ashes of the old. Nobel laureate Roger Penrose even speculates that at this point, the laws of physics might forget their own past, allowing a fresh start with reset constants. Critics pounce on two flaws. First, observations show the universe accelerating apart, not slowing toward a collapse. Dark energy seems to be winning the tug of war against gravity, making a big crunch unlikely. Second, entropy reversal raises thorny questions. Would time literally run backward or just appear to from an outside perspective? If entropy decreases, would consciousness reverse too, trapping beings in a subjective loop where cause and effect flip? The late Stephen Hawking once argued that even in a collapsing universe, entropy might still increase, leaving no clean reset, just a chaotic, scrambled demise. Yet the allure persists. If Poincaré recurrence holds, then even without a crunch, the universe might still loop just on timelines so vast they dwarf human imagination. Every moment, every configuration could recur infinitely, like a cosmic déjà vu written into the fabric of reality. Whether through collapse or patience, the universe might be doomed or blessed to repeat. And that raises a chilling question. If time is cyclical, are we the first iteration or merely an echo of a pattern older than existence itself? The answer might lie not in the stars, but in the relentless, inscrutable march of entropy. Dark energy, the mysterious force accelerating the expansion of our universe, might not just be stretching space. It could be setting the stage for the most violent cosmic reset imaginable, the Big Rip. Picture this relentless expansion not as a gentle drift, but as a runaway tear in the fabric of reality itself. Galaxies would be ripped apart, stars torn from their orbits, and eventually, even atoms would disintegrate as dark energy's grip overwhelms all fundamental forces. But here's where it gets strange. Some theories suggest this catastrophic end might not be the finale. It could be the prelude to a quantum rebirth, where the universe bounces back into existence like a phoenix from the ashes of its own destruction. This idea emerges from loop quantum gravity, a framework that reimagines spacetime as a woven fabric of tiny, indivisible loops. Unlike classical physics, where singularities mark dead ends for equations, loop quantum cosmology proposes that gravity becomes repulsive at extreme densities, preventing total collapse, or in this case, total disintegration. When dark energy rips spacetime down to its smallest scales, these quantum loops could reach a breaking point, triggering a rebound. Think of it like stretching a rubber band until it snaps, only for it to reform instantly with a burst of energy. The Big Rip wouldn't be the end. It'd be the universe hitting rock bottom before quantum effects launch it into a new cycle. The ekpyrotic scenario offers another twist. Originally conceived as a colliding brains model where our universe is a membrane slamming into another in higher dimensional space, it's been adapted to cyclic dark energy models. Here, dark energy's acceleration isn't a one-way ticket to oblivion, but a phase in a grander cycle. As the universe nears the Big Rip, quantum fluctuations could seed a new Big Bang, with energy from the rupture fueling the next cycle. It's cosmic recycling on an unimaginable scale, destruction and creation intertwined, each feeding the other. Critics argue that dark energy's nature is still too poorly understood to make these claims concrete. Is it truly constant, or could it evolve over time, weakening before reaching rip-scale violence? Observations of distant supernova and galaxy clusters might hold clues. If dark energy's strength changes, it could mean the difference between an eternal, lonely expansion and a universe that tears itself apart only to stitch itself back together. The implications are staggering. If the Big Rip leads to a bounce, then time loops aren't gentle resets their violent revolutions, with each iteration born from the wreckage of the last. Our universe's accelerating expansion might not be a countdown to silence, but the first act of a drama where destruction and rebirth are one and the same. And if loop quantum gravity or ekpyrotic models are right, the evidence might be written in the very fabric of spacetime, waiting for us to decipher its explosive handwriting. Primordial black holes, hypothetical relics from the universe's violent infancy, might be more than just cosmic anomalies. What if they're the leftover remnants from a previous cosmic cycle? Cosmic crumbs scattered across spacetime that helped shape the universe we know today. This theory suggests that when the last iteration of reality reached its end, not everything was erased. Instead, tiny black holes, some no heavier than an asteroid, could have survived the transition, lurking in the newborn cosmos like seeds waiting to sprout. As the new universe expanded, these primordial black holes would have acted as gravitational anchors, pulling matter together to form the first stars, galaxies, and the vast cosmic web we observe. But here's where Hawking radiation comes in. These ancient black holes wouldn't last forever. Over incomprehensible stretches of time, they'd slowly evaporate, leaking particles back into the void through quantum effects. This evaporation wouldn't just be a quiet fade out. It could be the key to recycling spacetime itself. As a black hole shrinks, the energy it releases isn't just heat. It's spacetime shaking loose from the black hole's grip, space itself being unmade and remade. In this view, a dying black hole isn't an end, it's a return, a transfer of information back into the fabric of the universe. The matter it once swallowed might not return in the same form, but the underlying structure of reality could inherit its imprint, like scars guiding the next cycle's growth. The implications are staggering. If true, primordial black holes could be more than ancient relics, they'd be cosmic architects. Their distribution in the early universe might explain why galaxies cluster in certain patterns, why voids exist between them, even why dark matter seems to shape the cosmos invisibly. Some theorists suggest these black holes are dark matter, not exotic particles, but hidden gravitational traps from a universe that came before. As they decay, they could be seeding quantum fluctuations that birth new black holes in turn, creating an eternal loop where destruction and creation feed each other across eons. Critics point to the lack of direct evidence. No one has definitively detected a primordial black hole, but their fingerprints might be hiding in gravitational wave data or the subtle distortions of ancient light. Others argue that Hawking radiation alone can't fully recycle a universe, that some information must be lost, breaking the cycle. Yet if the math holds, these tiny black holes could be the missing link between one cosmic loop and the next, stitching time together in ways we're only beginning to grasp. The universe might not just repeat, it could be growing from the bones of its ancestors, with black holes as both its gravestones and its cradle. Imagine a clock that ticks forever without winding down, a structure so strange it defies the universe's relentless push toward disorder. This isn't science fiction, it's the mind-bending reality of time crystals, a quantum phenomenon that could act as cosmic clockwork, anchoring time loops across the universe. Nobel laureate Frank Wilczek first proposed these exotic structures in 2012, envisioning systems that oscillate in a repeating cycle without energy input, like a perpetual motion machine operating on the rules of quantum mechanics. Unlike ordinary crystals where atoms arrange in repeating patterns in space, time crystals exhibit periodicity in time. Their components flip states rhythmically, locked in a dance that persists even at absolute zero. If such structures exist on a universal scale, they might be the hidden gears keeping cosmic cycles in sync, ensuring each loop begins exactly where the last one ended. The key to time crystals lies in their defiance of equilibrium. Most systems in nature settle into a static state when energy dissipates, like a pendulum eventually going still. But time crystals are quantum objects trapped in eternal oscillation, thanks to a quirk called many-body localization. Picture a row of magnets that keep flipping north to south in perfect sequence, not because they're powered, but because quantum entanglement locks their rhythm. This self-sustaining order makes them ideal candidates for cosmic timekeepers. If woven into the fabric of space-time, they could act like metronomes for the universe, marking the beats between cycles with inhuman precision. Critics initially dismissed time crystals as impossible, violating thermodynamics by creating perpetual motion, but experiments in 2017 proved Wilczek right. Scientists used chains of trapped ions or diamond defects to create microscopic versions, observing their rhythmic behavior under laser pulses. At larger scales, though, the implications grow staggering. If time crystals formed in the early universe, or perhaps in the searing plasma of the Big Bang or the extreme gravity near black holes, they might still be humming quietly today, their oscillations subtly guiding the universe's recurrence. Wilczek himself speculated that time crystals could be relics of a prior cosmic cycle, their patterns surviving the reset of a big bounce. Like a phonograph needle stuck in the groove of a record, they'd ensure each iteration of reality plays out with eerie similarity. This wouldn't just explain cosmic loops, it might answer why physical constants are so finely tuned for life. If time crystals remember certain configurations across cycles, they could nudge each new universe toward stability, like a chef tweaking a recipe over generations. Yet mysteries remain. Could time crystals really influence something as vast as space-time? Some models suggest networks of these structures might form a lattice-like framework, with oscillations propagating across cosmic distances. Others propose they're hiding in plain sight, their effects masquerading as dark energy or anomalous gravitational waves. Either way, their existence hints at a universe far more structured, far more intentional than we ever imagined. If time loops are real, time crystals might be the silent conductors keeping the symphony on beat. And if we learn to listen, their rhythm could reveal whether history is destined to repeat, or if the next loop holds a variation we've never heard before. What if time isn't a one-way river, but a mirrored corridor where every moment splits into two directions, past and future, meeting at a single pivotal point? This is the heart of Julian Barber's Janus point hypothesis, a radical reimagining of time loops that turns cosmic symmetry into a fundamental feature of reality. Named after the two-faced Roman god of transitions, the Janus point describes a singularity where time branches like a forked path, with the universe expanding symmetrically in both directions. In this model, the Big Bang isn't a beginning. It's a midpoint, a cosmic hinge where two mirror universes unfold in opposite temporal directions. Barber's theory emerges from the Wheeler-DeWitt equation, a cornerstone of quantum gravity that notoriously lacks a time variable. If time isn't baked into the universe's deepest equations, Barber argues, then our perception of its flow might be an illusion, a shadow cast by something far stranger. The Janus point reshapes this idea, suggesting that what we call time's arrow is just perspective. From the singularity, reality splits like a droplet hitting a surface, with one half evolving forward into what we experience as our universe, and the other half evolving backward into a mirror cosmos where entropy decreases. To observers in each branch, their timeline feels normal, but the Janus point itself is timeless, a frozen fulcrum balancing two mirrors of existence. Picture a film reel spliced at the midpoint, with both halves playing simultaneously in reverse of one another. In one universe, stars coalesce from dust, in the other, they dissolve into it. Yet neither is the right direction, both are equally valid, like reflections in a two-way mirror. This symmetry resolves a haunting question: why does time flow at all? The Janus point answers that it doesn't, not fundamentally. The flow is relative, an emergent property of our position in the loop. The implications are staggering. If the Janus point holds, then our universe might have a twin where causality runs backward, with effects preceding causes. Black holes in our world could be white holes in theirs, spewing matter instead of consuming it. Life in the mirror universe would perceive our timeline as inverted, their memories forming as their future unfolds. And if the two branches eventually recollapse, a possibility Barber entertains, they might rebound into new Janus points, creating fractal layers of mirrored time loops. Critics argue this model strains intuition, but its elegance lies in its economy. It doesn't invent new physics, it reinterprets existing equations to erase the need for a beginning or end. The Wheeler-DeWitt equation's timelessness isn't a bug. It's a feature, hinting that time is a local phenomenon, not a universal constant. The Janus point simply embraces this, weaving symmetry into the cosmos's DNA. If Barber is right, the evidence might hide in the universe's large-scale structure. A mirrored cosmos would leave subtle fingerprints, perhaps patterns in the cosmic microwave background, or anomalies in the distribution of matter. Finding them would mean discovering not just another universe, but our own reflection, staring back from the other side of time. And that raises a dizzying possibility. What if the echoes we've been searching for aren't from past cycles, but from our twin, living our future in reverse? The Janus point doesn't just loop time, it folds it, leaving us to wonder which side of the mirror we're really on. Phantom energy, the most extreme and unsettling flavor of dark energy, doesn't just push the universe apart. It shreds it. Unlike ordinary dark energy, which accelerates expansion at a steady pace, phantom energy grows stronger over time, its repulsive force becoming infinite in a finite future. The result, a cosmic doomsday so violent it doesn't just end the universe, it resets it. Picture space-time stretched so thin that galaxies, stars, even atoms are torn apart in a final, cataclysmic event known as the Big Rip. But what if this annihilation isn't the end? What if the very fabric of reality, frayed to its limits, becomes the seed for a new cosmic cycle? Robert Caldwell, the physicist who first modeled phantom energy's destructive potential, painted a grim timeline. Within tens of billions of years, this exotic energy could rip apart galaxy clusters, then solar systems, then planets until space-time itself fractures at the quantum level. But hidden in Caldwell's equations is a tantalizing possibility. When phantom energy tears space-time down to its smallest scales, quantum gravity effects might take over, triggering a bounce. Think of it like a rubber band snapping, except the snap births a new universe. The infinite density at the moment of rupture could mimic the conditions of the Big Bang, launching a fresh cycle from the ashes of the old. This idea dovetails with loop quantum cosmology, which suggests that quantum effects prevent true singularities. Instead of vanishing into nothingness, the collapsing universe reaches a minimum volume, then rebounds. Phantom energy's rip wouldn't be a dead end, it'd be a violent rebirth mechanism, with quantum fluctuations in the wreckage seeding the next universe's structure. The eerie symmetry, the very force that destroys reality, could also be the architect of its renewal. Critics argue phantom energy is speculative. No observational evidence confirms its existence. Yet if it's out there, its fingerprints might hide in the redshift of supernova or the clustering of galaxies. Future telescopes could spot anomalies in cosmic expansion, hinting at dark energy's phantom variant. And if they do, we're left with a paradox. The universe's most destructive force might also be its most creative, a cosmic destroyer and rebuilder woven into the same fabric. The Big Rip wouldn't just be an apocalypse, it could be the universe's way of hitting refresh, a cataclysm so total it loops back to zero. The implications stretch beyond physics. If phantom energy drives cyclical rebirth, then time loops aren't gentle or inevitable, they're forged in violence, each cycle born from the total annihilation of the last. It's a vision of the cosmos where endings and beginnings are the same event, where destruction isn't just necessary, it's sacred. And if Caldwell's math holds, the universe isn't just expanding toward oblivion, it's racing toward its own resurrection. Picture our universe not as a solitary bubble drifting in nothingness, but as one thin membrane floating in a higher dimensional expanse, like a sheet of paper drifting in a breeze. Now imagine another membrane, another universe floating toward ours. When they collide, the impact isn't destruction, it's rebirth. This is the spine-tingling premise of brain collision cycles, a theory where universes don't just loop. They rebound like cosmic drums, their collisions echoing across higher dimensions in endless cycles of creation. At the heart of this idea lies M-theory, the elusive framework that unites string theory's tangled threads. Here, our universe isn't a standalone entity. It's a three-dimensional brain, short for membrane, embedded in an 11-dimensional bulk. Other brains might drift through this bulk, invisible to us yet just as real. When two brains collide, the energy of their impact could ignite a new Big Bang, not as a solitary explosion, but as a ripple spreading across the membrane surface. The result, a universe reborn from the shockwaves of a higher dimensional crash. Physicists Paul Steinhardt and Neil Turok refined this into the ekpyrotic model, named after the ancient Greek word for conflagration, a fire that purifies and renews. Unlike traditional cyclic theories relying on a big crunch, brain collisions avoid the pitfalls of infinite density. The brains don't collapse, they merely kiss and recoil, trading kinetic energy for raw creation. Picture two sheets of metal clanging together. The sound they produce isn't just noise, it's a transfer of energy. In the ekpyrotic scenario, that energy becomes matter, radiation, and the very fabric of space-time. The big splat isn't messy, it's precise, seeding a new universe with conditions eerily similar to the last, but with subtle quantum variations. Why would this produce cyclic time loops? Because the brains don't vanish after colliding. Like pendulums, they'd swing apart in the bulk, only to be drawn back together by higher dimensional forces, perhaps a form of dark energy acting across dimensions. Each collision resets entropy, solving the problem of ever-increasing chaos that plagues other cyclic models. The brains are cosmic etch-a sketches. When they meet, the slate is wiped clean, yet faint imprints, quantum fluctuations from past cycles, might linger, shaping the next iteration's galaxies and voids. Evidence might lurk in gravitational waves. If a previous brain collision sent ripples through space-time, future observatories could detect their faint whispers in the cosmic microwave background's polarization. Even more provocatively, the ekpyrotic model predicts a smoother, more uniform early universe than traditional inflation, a signature astronomers could test by mapping primordial gravitational waves. Critics argue that higher dimensions remain speculative and brain dynamics are notoriously hard to test, yet the elegance of the idea is undeniable. It replaces cosmic singularities with collisions, entropy problems with symmetry, and lonely universes with a hidden multiverse dancing in dimensions beyond our sight. If Steinhardt and Turok are right, time loops aren't just echoes, they're the rhythm of brains moving to a song written in 11 dimensions, a song we're only beginning to hear. Neutrinos, those ghostly particles that slip through planets like they're not even there, might be more than just cosmic background noise. What if they're messengers from past universes, whispering secrets from loops long gone? This theory hinges on their strangest quality, their near invisibility. Neutrinos barely interact with matter, passing through trillions of atoms without a trace. But that's exactly what makes them the perfect time capsules. While photons from the Big Bang get scattered and altered over billions of years, neutrinos from the earliest moments could travel unscathed, carrying pristine information from a previous cycle. Think of it like finding an ancient letter sealed in glass. Most documents decay, but this one survives untouched. Now imagine that letter was written not just centuries ago, but in a prior iteration of reality. If the universe loops, neutrinos might be those unopened letters, their weak interactions acting as a cosmic shield, preserving data from before the reset. Some models suggest that during a big crunch or bounce, the dense, searing conditions would generate staggering numbers of neutrinos. If even a fraction survived the transition, they'd flood the newborn universe like echoes in a canyon. The real kicker, we might already be detecting them. Neutrino observatories like Ice Cube in Antarctica catch high-energy neutrinos from deep space, some with energies so extreme their origins are unknown. Could a handful of these outliers be relics from a pre-Big Bang universe? The idea isn't as far-fetched as it sounds. Quantum mechanics allows for particles to tunnel through seemingly impassable barriers, like the singularity between cycles. If neutrinos did this, their properties might encode subtle anomalies, unusual energy distributions, unexpected oscillation patterns, or even correlations in arrival directions that defy astrophysical explanations. Critics argue that without a clear signature, these claims are speculative at best, but proponents point to the cosmic neutrino background, a sea of low-energy neutrinos from the early universe, as a potential testing ground. If loops imprint unique fluctuations on this background, future detectors like Ptolemy could spot them. Others suggest hunting for sterile neutrinos, hypothetical particles that don't interact at all except via gravity. These could be the ultimate time travelers drifting between cycles like shadows. The implications are staggering. If neutrinos archive past universes, decoding them could answer questions we've barely dared to ask. Did physical constants vary between cycles? Did structures form differently? Are there echoes of civilizations lost to cosmic reboots? The universe might not just loop, it could be quietly chronicling its own history in particles we're only learning to read. And if we listen closely, those faint, ghostly signals might tell us we're not the first iteration or the last. At the very heart of our universe, hidden behind the veil of the Big Bang, there might be a celestial object so bizarre it defies all conventional physics, a Planck star. This isn't a star in the traditional sense, blazing with nuclear fire. Instead, think of it as a quantum gravity time bomb, a relic of such incredible density that it pauses right at the brink of becoming a black hole, held back by the repulsive force of loop quantum gravity. According to this radical theory, the Big Bang wasn't the beginning. It was the explosive rebirth of a Planck star from a previous cosmic cycle, and its rhythmic pulsations could be the engine driving eternal time loops. The concept emerges from loop quantum cosmology, a framework that reimagines the universe's birth not as a singularity, a point of infinite density where physics breaks down, but as a quantum bounce. Here's how it works. When a massive star collapses into a black hole in one universe, it doesn't vanish into a singularity. Instead, quantum gravity effects kick in, compressing matter to a Planck-scale density before triggering a violent rebound, like a supernova in reverse. This rebound creates a Planck star, a fleeting, ultra-dense object that lingers for microseconds before exploding outward, birthing a new universe in its wake. The mind-bending implication: our entire cosmos might be the expanding debris of a Planck star's detonation, and the black holes we observe today could be incubators for future universes, each carrying the seeds of the next cycle. What makes Planck stars so tantalizing is their potential to solve one of cosmology's biggest headaches, the black hole information paradox. In classical physics, anything swallowed by a black hole is lost forever, violating quantum mechanics' rule that information can't be destroyed. But if black holes are actually Planck stars in disguise, then the information isn't lost, just trapped, waiting to be released in the next cosmic cycle. Imagine a library where every book ever burned is actually stored in a vault, only to be reprinted when the universe reboots. The kicker: we might already have evidence. Some models suggest that when a Planck star finally explodes, it could leave behind faint imprints in the cosmic microwave background, subtle temperature fluctuations or circular patterns akin to Penrose's Hawking points. Others speculate that gamma-ray bursts, those mysterious flashes of high-energy light from the distant universe, could be the dying screams of Planck stars from a prior cycle. Even more provocatively, if loop quantum cosmology is correct, then the universe's expansion isn't slowing down or speeding up randomly. It's following the residual momentum of that primordial bounce, like a pendulum swinging from one cosmic epoch to the next. But here's where it gets truly dizzying. If Planck stars drive these cycles, then time loops aren't just cosmological, they're quantum mechanical. Each black hole in our universe could be a portal to a new timeline, with Planck stars acting as cosmic reset buttons. Instead of a single, uniform loop, we might live in a fractal multiverse, where every collapse and rebound spins off a fresh reality with slightly tweaked physical laws. Some universes might thrive, producing countless black holes and thus countless offspring. Others might fizzle out, their Planck stars too feeble to reignite. It's Darwinian evolution on a multiversal scale, where the fittest universes are the ones that birth the most black holes. Critics argue that Planck stars remain hypothetical, their existence untested. Yet their promise is undeniable. They bridge the gap between quantum mechanics and general relativity, offer a way out of the singularity problem, and provide a tangible mechanism for cosmic recycling. If future telescopes detect anomalies in the cosmic microwave background, or if gravitational wave observatories pick up echoes from black hole mergers that hint at something lurking inside, we might finally confirm that the universe isn't just looping. It's breathing, inhaling collapsed stars, exhaling new realities over and over in a rhythm as old as time itself. And if that's true, then the deepest mysteries of existence might not lie in the distant past or far future, but in the quantum heart of a star we've yet to see. What if reality itself is shaped not by stars or atoms, but by the act of observation, by consciousness turning possibility into existence? This radical idea, rooted in ancient Eastern philosophies and modern quantum theory, suggests that time loops might not be baked into the cosmos but threaded through our collective awareness. The von Neumann-Wigner interpretation takes this even further, proposing that consciousness isn't just a bystander in the universe, it's the sculptor, collapsing quantum probabilities into concrete reality with every thought and observation. Merge this with the Hindu concept of kalpas, vast cycles of creation and destruction driven by cosmic consciousness, and you get a spine-tingling possibility. What we call time loops could be the universe's way of rehearsing until it gets the story just right, with consciousness as both the audience and the director. Picture reality as a film reel with infinite possible frames. Quantum mechanics tells us particles exist as probabilities until measured like unprojected film waiting for a projector's light. The von Neumann-Wigner interpretation argues that projector is us. Every observation, every conscious act locks one frame into place, advancing the cosmic narrative. Now imagine this process looping. If consciousness governs reality's flow, could it also govern its repetition? Ancient Buddhist texts describe samsara, the wheel of rebirth, where souls cycle through existences until enlightenment breaks the loop. Translate that into physics, and you get a universe where quantum states reset, not because of gravity or entropy, but because conscious observers, whether human, alien, or something stranger, haven't yet solved the ultimate puzzle of existence. The evidence might already be hiding in plain sight. Quantum entanglement, where particles instantaneously mirror each other across vast distances, hints at a universe deeply interconnected, as if woven by a single observing mind. The famous double-slit experiment shows particles behaving as waves until observed, then choosing a definite state. Extend this to cosmic scales, and the universe itself might only take shape when observed, with each cycle refining the observation like a painter reworking a canvas until the vision matches the intent. Even the eerie uniformity of the cosmic microwave background could be a signature of this cycle, a universe observed into coherence over countless iterations. Critics dismiss this as mysticism masquerading as science, pointing out that consciousness remains poorly defined. Yet pioneers like Eugene Wigner argued that ignoring the observer's role leads to paradoxes even math can't resolve. If they're right, time loops aren't accidents of physics, they're rituals of perception. Every loop might bring the universe closer to a shared realization, a cosmic aha moment where consciousness finally collapses the ultimate probability, a reality that no longer needs to repeat. Until then, we're both the experimenters and the lab rats, trapped in a maze of our own making, wondering if the exit was there all along, waiting to be seen. Black holes consume, but they're theoretical opposites. White holes may be the universe's recycling centers, spewing out matter from previous cosmic cycles like cosmic fountains. While black holes trap everything past their event horizons, white holes, if they exist, would violently expel energy and matter in a process that could resemble the Big Bang itself. Picture a singularity not as a one-way trapdoor, but as a revolving door, a gateway where matter swallowed by black holes in one era gets ejected by white holes in another, seeding new universes with the remnants of the old. This isn't just theoretical poetry. It's a cornerstone of big bounce cosmologies, where the universe cycles through endless expansions and contractions, with white holes acting as the mysterious reset buttons between each iteration. The math behind white holes emerges straight from Einstein's equations. Their black holes run backward in time. Where a black hole's event horizon marks a point of no return, a white hole's horizon would be a point of no entrance, repelling all matter and energy with irresistible force. Some theorists suggest that when a black hole collapses to its smallest possible size in one universe, quantum gravity effects could cause it to rebound as a white hole in another, spraying its contents into a newborn cosmos. This transformation wouldn't be instant. It might take trillions of years, far longer than our universe's current age, meaning the white holes we'd expect to see could be relics of universes long gone, flickering to life in the distant future of our own timeline. The implications for time loops are staggering. If white holes exist, they could be the universe's way of preserving information across cycles, solving one of the thorniest problems in physics, the black hole information paradox. Instead of data vanishing into oblivion, it's stored, compressed, and then rebooted into a new reality. Imagine a cosmic hard drive. Black holes write data, white holes read it back out, and the universe itself is the storage medium. This could explain why our cosmos seems so finely tuned for complexity. Each cycle isn't starting from scratch. It's inheriting quantum fluctuations, ratios of forces, even the seeds of structure from the previous loop, refined over eons like a recipe perfected across generations. Some Big Bounce models take this further, suggesting that the Big Bang wasn't the absolute beginning but the moment a white hole from a prior universe erupted into ours. The sudden, explosive ejection of matter and energy would look identical to the singularity we call the birth of space-time, but with a crucial difference. It's not creation ex nihilo, it's rebirth from the ashes. This idea gains traction in loop quantum gravity, where singularities are replaced by quantum bounces, avoiding infinite densities by allowing spacetime to fold rather than break. In this view, every black hole collapse is a potential white hole birth, every death a prelude to resurrection on a cosmic scale. But why haven't we seen white holes? If they're out there, they'd be incredibly rare, their lifespans fleeting compared to black holes. Some physicists speculate that gamma-ray bursts, those brilliant, mysterious flashes in distant galaxies, could be white holes blinking into existence, their energy output matching predictions for a singularity's final outburst. Others suggest that dark matter itself might be composed of primordial white hole remnants, their gravitational influence felt but their light long since faded. The most tantalizing possibility is that white holes aren't in our past or present, but our future, waiting in the far reaches of time to become the engines of the next cycle. Critics argue that white holes violate thermodynamics, ejecting energy without an obvious source. Yet if they're connected to black holes via higher dimensions or quantum tunnels, the energy balance might hold across the multiverse. It's a cosmic sleight of hand. What seems lost in one universe reappears in another, with white holes as the magicians pulling matter from their celestial hats. Whether they're real or just mathematical curiosities, their role in time loop theories forces us to confront a profound truth. The universe might not just repeat but remember. And if it does, the echoes of past cycles could be hiding in the darkest corners of spacetime, waiting for the right moment to erupt back into existence. The strangest way to freeze time might not involve black holes or cosmic collisions, just the act of watching. At the quantum level, observation isn't passive, it's transformative. The quantum Zeno effect reveals that simply measuring a system can lock it in place, like a flickering light bulb staying lit if you check it fast enough. Named after the ancient Greek philosopher's paradox about motion being an illusion, this phenomenon suggests that reality itself might pause under relentless scrutiny. Now imagine scaling this up. If the entire universe were under constant observation, could time itself seize up, then reset, like a cosmic pause button pressed by an unseen hand? The mechanics are just as mind-bending as the implications. In experiments with trapped ions, atoms suspended in electromagnetic fields, physicists observed something eerie. When these ions were bombarded with rapid-fire measurements, their quantum state stopped evolving. Normally, particles decay or shift states unpredictably. But under ceaseless observation, they froze like deer in headlights trapped in a quantum stasis. This isn't just laboratory curiosity, it's proof that measurement changes reality. Extend this principle to cosmological scales, and you get a radical vision of time loops where the universe's flow depends on being watched. What could possibly observe the whole cosmos? Some theorists speculate about a universal observer, perhaps a quantum field, a higher dimensional entity, or even the collective consciousness of all living beings. Others suggest it's simpler: quantum decoherence, the process by which particles interact with their environment, acts as a form of passive observation. Every photon collision, every gravitational tug, becomes a measurement that nudges the universe's timeline forward or holds it in place. If these interactions were to synchronize in a specific rhythm, time might fracture into discrete frames like a film reel advancing one frozen instant at a time. The most unsettling possibility, we might be living in such a loop right now. If the universe's expansion is punctuated by quantum observation events, perhaps tied to black hole emissions or vacuum fluctuations, then what we perceive as the arrow of time could be a series of quantum freezes and restarts. Each tick of cosmic time would be a snapshot, a frozen frame briefly observed into existence before collapsing into the next. The Big Bang wouldn't be a singular explosion, but the latest frame in an infinite reel, each cycle triggered by the universe observing itself into a new state. Critics argue that scaling the quantum Zeno effect from ions to galaxies is a leap too far, yet the underlying math is agnostic to size. If observation can stall a single atom's decay, why not a star's collapse or spacetime's expansion? The answer might lie in the very fabric of reality. If quantum mechanics governs all scales, then time itself could be a tapestry woven from countless observations, its loops not accidents, but artifacts of a universe perpetually catching its own reflection. And if that's true, the next cosmic reset might not need a black hole or a big crunch, just a moment when the universe blinks and forgets to look away. Picture the universe not as a vast expanse of stars and galaxies, but as a flickering screen, a two-dimensional surface projecting every event we experience as a three-dimensional illusion. Now imagine that screen periodically refreshing, like a cosmic monitor rebooting frame by frame. This is the startling premise behind holographic boundary resets, where time loops aren't smooth cycles but discrete jumps, like flipping through pages of a cosmic flipbook where each page is a complete iteration of reality. At the quantum level, spacetime might not be continuous at all, but pixelated, with each pixel representing the smallest possible unit of reality. When the universe reaches the edge of one computational frame, it snaps to the next, creating the illusion of flowing time while fundamentally operating in discrete steps. Nobel laureate Gerard T. Hooft laid the groundwork for this idea by merging quantum mechanics with holography, showing how all the information in a volume of space, every particle collision, every supernova, could be perfectly encoded on its boundary surface. It's like projecting a three-dimensional movie from a two-dimensional DVD, but T. Hooft's real breakthrough was suggesting these holograms aren't static. They update in quantized ticks governed by Planck scale physics. Each update isn't just a minor adjustment, it's a full reset, recalculating the entire universe from its boundary data. Think of it like a video game engine rendering each frame from scratch, where the next loop isn't predetermined but freshly computed based on the previous frame's final state. The implications warp our understanding of causality. If time advances in these discrete hops, then what we perceive as the flow of time might be a series of cosmic freeze frames, with infinitesimal gaps between them where reality briefly winks out before rebooting. This could explain quantum indeterminacy, those moments when particles seem to exist in multiple states at once. They're not oscillating, they're loading between frames, trapped in a buffer until the next refresh locks them into place. Even black holes fit this model. Their event horizons might act like error correction boundaries, ensuring no data is lost when the universe resets, preserving information across loops like a cosmic control plus S. Evidence for this radical vision might lurk in the fabric of spacetime itself. If the universe is pixelated, there should be a fundamental limit to how precisely we can measure distance or time, a graininess to reality. Experiments like GEO 600, a gravitational wave detector in Germany, have detected unexplained noise at tiny scales that some physicists speculate could be the fuzz of spacetime's underlying pixels. Others propose that gamma-ray bursts, the most energetic events in the cosmos, might carry imprints of these refreshes in their light spectra, subtle glitches revealing the universe's rendering rate. Critics argue that holographic resets sound more like computational metaphors than testable physics, but recent work in quantum gravity suggests otherwise. In simulations using tensor networks, mathematical structures that represent space-time as interconnected nodes, researchers have found that emergent universes naturally exhibit holographic properties, with boundary data determining interior events. It's as if the cosmos runs on cosmic blockchain technology, with each block being a snapshot of the universe, cryptographically linked to the one before it. If our reality operates similarly, then time loops wouldn't be accidents of physics, they'd be features of the system, built into the universe's operating code. The most haunting question isn't whether this model is possible, but what it means for free will. If each loop is a recomputation based on prior states, are our choices truly ours or just outputs of an equation we can't see? The holographic boundary doesn't answer. It just keeps recalculating frame by frame, turning the universe into the most profound animation ever rendered. And if T. Hooft is right, the next loop might already be loading pixel by pixel on the edge of everything we know. Deep beneath the fabric of reality, where the quantum fields that govern existence hum in perfect equilibrium, there might be a cosmic trapdoor waiting to snap shut, a phenomenon so catastrophic it wouldn't just end the universe, but rewrite the rules of physics in an instant. This is the nightmare scenario of vacuum metastability collapse, where the very ground beneath our feet, not the Earth but the quantum vacuum of space-time itself, could be perched on a precarious ledge, one quantum nudge away from dissolving into oblivion. The culprit, the Higgs field, the same invisible force that gives particles mass, might not be sitting in its most stable configuration. Instead, it could be trapped in a false vacuum, a temporary low-energy state, like a marble resting in a shallow dent atop a hill, waiting for the slightest push to roll into the true valley below. What happens if that marble drops? The collapse would begin with a single, random quantum fluctuation, a tiny bubble of true vacuum forming somewhere in space. Inside this bubble, the Higgs field would snap into its lowest energy state, radically altering the laws of physics. The speed of light, the strength of gravity, even the behavior of atoms would be rewritten instantly. This bubble would expand outward at nearly light speed, its walls a crushing wave of annihilation. Every star, every planet, every molecule it touched would cease to exist as we know it, reconfigured into something unrecognizable. The universe wouldn't just end, it would reboot with physics so alien that concepts like matter or life might have no meaning at all. The math behind this apocalypse is chillingly solid. Current measurements of the Higgs boson's mass suggest the field could indeed be metastable, hovering just above a deeper energy well. Particle colliders like the Large Hadron Collider have narrowed the odds, but the uncertainty remains. Our universe might be stable for billions of years, or it could already be teetering on the edge. Some calculations even suggest that if a high-energy cosmic ray struck the right quantum fluctuation, it could trigger the collapse prematurely, a cosmic game of Russian roulette where the gun is pointed at all of existence. Yet there's a twist that ties this doom scenario back to time loops. If a bubble of true vacuum forms, it wouldn't just erase everything, it might spawn a new universe in its wake. The energy released during the collapse could ignite a new Big Bang inside the bubble, with physics reset to a fresh set of constants. In this view, vacuum decay isn't just destruction. It's a cosmic reset button, a way for reality to shed its old skin and emerge reborn. Some theories even speculate that this has happened before, that our own universe is the product of a previous vacuum collapse, its physics fine-tuned by the explosive aftermath of a parent universe's demise. The most haunting question isn't whether this could happen, but whether it already has. If bubbles of true vacuum are expanding somewhere in the cosmos, their light hasn't reached us yet, a silent wave of annihilation that could already be on its way. And if the cycle repeats eternally, with each collapse birthing a new universe, then time itself might be a series of failed experiments, a cosmic lab where physics tweaks its parameters until something sticks. The Higgs field's instability isn't just a threat, it could be the engine of cosmic evolution, a reminder that even the laws of nature are not set in stone, but in flux, waiting for the next roll of the dice. What if the universe isn't just looping, it's folding, repeating itself in infinite layers like a cosmic origami, where every scale hides another version of the whole? This is the hypnotic premise of fractal universe recursion, a theory that marries the mind-bending patterns of mathematics to the vast architecture of spacetime. Picture the Mandelbrot set, that infinite swirl of self-similar shapes where zooming in reveals endless iterations of the original design. Now imagine that same principle governing reality itself, with galaxies, stars, and even atoms echoing the structure of the larger cosmos like nested dolls carved from the fabric of existence. The roots of this idea stretch back to scale relativity, a radical framework pioneered by physicist Laurent Nottale. In conventional physics, relativity applies to motion, how objects behave at different velocities. But Nottale asked, what if relativity also applies to scale? Just as Einstein showed space and time are fluid, scale relativity suggests the universe has no fixed zoom level. Instead, it operates in a fractal-like state where physical laws subtly shift depending on whether you're observing galaxies or quarks. At certain scales, these shifts could create loops, tiny eddies in the fabric of reality where conditions mirror those of the larger cosmos, like ripples in a pond echoing the shape of the waterfall that created them. The implications are staggering. If the universe is fractal, then time loops might not be monolithic events but layered phenomena, with small-scale cycles ticking away inside larger ones. A black hole's singularity could harbor a micro-universe with its own laws, cycling through births and deaths on timescales imperceptible to us. Even the Big Bang might not be unique, just one inflection point in an infinite regression of expanding and contracting layers, each with its own version of history. It's as if reality is a hall of mirrors where every reflection contains another world, and every world contains another reflection, ad infinitum. Evidence for this mind-bending structure might hide in the cosmic microwave background. Just as the Mandelbrot set reveals intricate patterns at every magnification, the CMB's fluctuations could encode signatures of fractal geometry clusters within clusters, echoing across scales. Some researchers have already spotted statistical anomalies in the CMB's temperature variations that defy randomness, hinting at a deeper, nested order. Others point to the large-scale distribution of galaxies, which eerily resembles neural networks or bacterial colonies, structures known for their fractal properties. Critics argue that fractal cosmology risks being untestable, a beautiful metaphor without empirical teeth. Yet proponents counter that scale relativity makes concrete predictions, like subtle deviations in the behavior of particles at extreme energies or gravitational waves exhibiting fractal-like harmonics. If verified, these clues could reveal a universe far stranger than we imagine, and not just looping but unfolding, its history written in spirals within spirals, cycles within cycles. The deepest question isn't whether we're in a time loop, but which layer of the loop we're even perceiving. Are we the universe or just a flicker in its recursive dream? The answer might depend on how closely we dare to zoom in or out. At the smallest scales imaginable, far beneath atoms, deeper than quarks, spacetime itself might not be the smooth, unbroken fabric we perceive. Instead, it could be a churning, frothing ocean of quantum foam, where tiny loops of spacetime constantly blink in and out of existence like bubbles in a boiling pot. This surreal landscape, first proposed by physicist John Wheeler, suggests that the very foundation of reality is a seething chaos of microscopic wormholes, virtual particles, and fleeting distortions where the rules of gravity and quantum mechanics collide. In this foamy underworld, time and space lose all meaning, fracturing into a probabilistic dance where cause and effect tangle into knots. But what if these quantum foam bubbles aren't just random noise? What if they're the seeds of cosmic-scale time loops, with each micro-loop stacking like building blocks until the entire universe is caught in a self-repeating cycle? Wheeler's spacetime foam isn't just poetic imagery, it's a mathematical inevitability when you push Einstein's equations to the Planck scale, where distances shrink to a trillionth of the size of an atom. At these scales, Heisenberg's uncertainty principle wreaks havoc, allowing energy to fluctuate wildly enough to warp spacetime itself into temporary loops. Picture a stormy sea where every crashing wave spawns tiny whirlpools, each one a self-contained vortex twisting back on itself. Now replace the water with spacetime and the whirlpools with Planck-length wormholes, and you've got quantum foam, a universe bubbling with ephemeral loops that could, under the right conditions, amplify into something far grander. This is where loop quantum gravity takes the baton. Unlike string theory's vibrating filaments, LQG imagines spacetime as a web of interconnected loop spin networks that weave together to form the geometry of reality. These loops aren't just abstract lines, they're quantized units of spacetime like pixels on a cosmic screen. When you zoom out, their interactions create the illusion of smooth, continuous space and time, just as a movie blends still frames into motion. But here's the twist. If these spin networks can twist into knots or braid together in certain configurations, they might produce larger, stable loops, time loops that persist beyond the quantum froth. Imagine 1,000 tiny eddies in a river merging into a single, powerful whirlpool, its rotation so entrenched it starts influencing the flow of the entire waterway. The implications are staggering. If quantum foam loops can coalesce into macro loops, then the universe might not need black holes or big bangs to reset itself. Time loops could emerge organically from the fabric of spacetime, like cracks forming in ice as it freezes and refreezes. This wouldn't just explain cyclical cosmologies, it could redefine what we mean by time altogether. In LQG, time isn't a background stage, it's a dynamic player emerging from the relationships between loops. A loop that circles back on itself wouldn't just bend time, it would be time, a closed curve where past and future stitch together seamlessly. Critics argue that quantum foam remains untestable, hidden behind an energy barrier far beyond our particle colliders, yet indirect clues might lurk in the shadows. Some models suggest that foam-like spacetime would subtly alter the paths of high-energy photons traveling across the universe, an effect we could detect in gamma-ray bursts. Others propose that gravitational wave observatories might one day pick up faint murmurs from Planck-scale vibrations, hints of the froth beneath our feet. Even more provocatively, if spacetime loops really do scale up, their gravitational echoes could imprint on the cosmic microwave background, leaving faint spiral patterns like fingerprints on glass. The most radical take, quantum foam loops might not just explain time loops, they could democratize them. Instead of a single, universe-spanning cycle, reality might be riddled with local loops like glitches in a cosmic recording. A star here, a planet there, even a single human life might, through some improbable braid of spin networks, stumble into a personal loop, a pocket of time that resets while the rest of the universe marches forward. It's a dizzying thought that the universe doesn't just loop as a whole, but in fragments like a broken mirror reflecting infinite variations of the same light. And if that's true, then somewhere in the quantum foam, another version of this moment might already be bubbling up, waiting to twist itself into existence all over again. What if the relentless flow of time, the feeling that moments slip inexorably from future to past, is nothing more than a trick of the mind? Einstein himself called this sensation a stubborn illusion, hinting at a radical truth hidden in his equations, the block universe. In this model, all of existence, every event, from the Big Bang to the heat death of the cosmos, is frozen in a four-dimensional tapestry where past, present, and future coexist simultaneously. Think of it like a movie already filmed. We're merely watching the frames unspool one by one, mistaking the progression of our attention for the movement of time itself. The block universe emerges naturally from relativity. Einstein showed that time isn't absolute, it stretches and compresses depending on motion and gravity. Two observers moving at different speeds will disagree on the timing of events, proving there's no universal now. This shatters the intuitive notion of time as a river flowing in one direction. Instead, spacetime becomes a static landscape where before and after are just coordinates like locations on a map. Your birth, your death, the collapse of the last star, all are equally real fixed points in the cosmic block. But why does time feel like it passes? Cognitive scientists propose that consciousness is a kind of projector beam scanning across spacetime, creating the illusion of flow. Our brains stitch together sequences of neural states, constructing a narrative from the static frames of reality. Like a reader tracing words on a page, we mistake our focus for the book's structure. Even memories reinforce the illusion. They're not records of a receding past, but data points we access within the block. The implications are dizzying. Free will becomes a puzzle. If the future already exists, are choices real or just predetermined coordinates we haven't perceived yet? Some philosophers argue that the block universe preserves agency by defining you as the entire world line of your life. Your decisions are baked into the tapestry, but no less yours. Others see it as proof of destiny, with every event locked in place like a fly in amber. Critics counter that the block model can't explain thermodynamics, why entropy always increases, creating time's arrow. But here's the twist: entropy might be a local phenomenon like weather on a planet. Just as Earth storms don't dictate the universe's climate, our perception of time's flow could be a side effect of how information organizes in our corner of spacetime. In regions near black holes or during cosmic inflation, the rules might differ entirely. Einstein's illusion challenges us to reconcile two truths: the mathematical elegance of a timeless universe and the visceral reality of our experience. Perhaps the answer lies in scale. Quantum processes unfold in a froth of uncertainty, while relativity paints the big picture. Between them, consciousness emerges, a flickering light in the block, mistaking its journey for the road. The universe isn't changing, we are, and in that realization lies the deepest mystery of all. If time doesn't flow, what does it mean to exist at all? Galaxies aren't just drifting apart in the cosmic expansion, some are moving together in a way that defies all known forces, as if pulled by an invisible hand from beyond the edge of the observable universe. This eerie phenomenon, dubbed dark flow, was first detected in 2008 when astronomers tracked the peculiar motions of hundreds of galaxy clusters. Instead of scattering randomly like leaves in the wind, these massive structures were streaming toward a single point in space at breakneck speeds, as though caught in a current no one could see. The culprit, one radical theory, suggests these clusters might be tracing the gravitational scars of a universe that existed before ours, tugged by the remnants of superstructures from a prior cosmic cycle. The evidence lies in the cosmic microwave background, the afterglow of the Big Bang. When galaxy clusters move, their hot gas scatters CMB photons in a telltale pattern called the kinematic Sunyaev-Zeldovich effect. By analyzing this distortion, researchers found clusters hurtling at over 1,000 kilometers per second toward the constellations Centaurus and Vela, a direction that shouldn't hold any unusual mass. Standard cosmology chalks this up to statistical flukes or measurement errors, but the persistence of dark flow across multiple studies raises a haunting question. What if this motion isn't random at all, but the echo of a gravitational imbalance left over from a predecessor universe? Imagine a lake frozen mid-wave, its surface preserving the ripples of a pebble tossed long before the ice formed. In the same way, if our universe emerged from a prior cycle, perhaps via a big bounce or black hole rebirth, the distribution of matter in that earlier cosmos might have imprinted asymmetries on spacetime itself. Superclusters larger than anything in our visible universe could have collapsed into black holes whose gravity still tugs at the fabric of reality, warping the trajectories of galaxies like shadows of long-dead giants. This wouldn't just explain dark flow, it'd mean we're sailing in the wake of a ghost cosmos, its fingerprints lingering at the edge of perception. Critics argue that dark flow could stem from local anomalies, a massive, distant supervoid or undiscovered physics in the early universe. Others suggest it's an artifact of our reference frame, like mistaking a train's motion for the landscape moving. But proponents like cosmologist Laura Mersini-Horton propose something far grander, that our universe is one bubble in a multiverse foam, and dark flow reveals the gravitational pull of neighboring universes pressing against our cosmic horizon. If true, these flows wouldn't just point to a past loop, they'd map the contours of a reality far larger than we ever imagined. The stakes are cosmic. If dark flow is real and externally caused, it shatters the principle that the observable universe is all we can know. It hints at a cosmos stitched together by threads stretching beyond time, where gravity itself remembers what came before. Future telescopes like the Euclid satellite could settle the debate by mapping galaxy motions with unprecedented precision. Until then, dark flow remains a tantalizing cipher, a message in the stars that might just read, "You are not the first." Deep in the equations of particle physics lies a tantalizing symmetry so perfect it could rewrite the rules of reality: supersymmetry. This elegant theory proposes that every known particle has a hidden twin, a superpartner lurking just beyond our detection. Electrons have selectrons, quarks have squarks, even force-carrying particles like photons have photinos waiting in the wings. But here's the mind-bending twist: these shadow particles might not just fill gaps in our models. They could be cosmic timekeepers, their very existence marking the transitions between universal loops. At supersymmetry's heart is balance, a symmetry so profound it could solve mysteries from dark matter's nature to the fragility of the Higgs boson. Yet in our universe, this symmetry is broken. We don't see photinos or squarks floating around. If they exist, they must be incredibly massive, requiring energies far beyond our colliders to produce. This broken symmetry might be no accident. Imagine a pendulum frozen mid-swing, its perfect arc interrupted. Now picture that pendulum as the universe itself, with supersymmetry's balance representing the reset point between cycles. Each time the cosmos loops, sussy particles could briefly flicker into existence, their decays acting like cosmic hourglass grains, each grain marking the passage from one cycle to the next. The mechanism is as beautiful as it is bizarre. In the searing heat of a big bang or big bounce, supersymmetric particles would dominate, their perfect symmetry restoring equilibrium to the quantum fields that govern reality. But as the universe expands and cools, that symmetry breaks, the superpartners decay into the particles we know, and the stage is set for stars, galaxies, and life. This phase transition isn't just a one-time event. If the universe cycles, it could happen over and over, with sussy breaking and restoration acting like the universe's heartbeat, each pulse a new beginning. Support for this vision comes from an unexpected place: dark matter. Many sussy models predict the lightest superpartner would be stable, a relic particle that outlasts all others. These particles could permeate the cosmos, forming the invisible scaffolding of galaxies. Now consider this: if dark matter is made of these leftover superpartners, it might not just be a passive bystander. It could be the cosmic memory bank, carrying quantum information from one cycle to the next. Like a computer's RAM preserving data through a reboot, dark matter's stability might allow it to remember the conditions of previous loops, subtly influencing each new universe's structure. Critics argue that supersymmetry's failure to appear in collider experiments casts doubt on the theory. Yet sussy allure persists because it solves too many problems to ignore. The Higgs boson's mass is unnaturally fine-tuned unless superpartners exist to cancel out quantum corrections. Gravity's weakness compared to other forces makes sense if spacetime has hidden supersymmetric dimensions. Even cosmic inflation, the universe's explosive early growth, could be driven by sussy particles called inflatons. The math is too elegant to dismiss. Perhaps we're simply looking for supersymmetry in the wrong way, not as particles to be discovered in our current cycle, but as markers of the transitions between them. Now imagine this cycle playing out. As the universe nears its end, whether through heat death or collapse, quantum effects could destabilize the vacuum, lowering the energy threshold until supersymmetry is temporarily restored. Superpartners would reappear, their decays releasing energy that helps trigger the next Big Bang. Like a phoenix that must first become ashes before rising anew, the universe might need to resymmetrize before it can reboot. Each loop wouldn't be an exact copy. Tiny variations in how sussy breaks could tweak physical constants, creating a multiverse of cycles where only the most stable, life-friendly iterations persist. The evidence might be hiding in plain sight. If sussy cycles imprint on the cosmic microwave background, future telescopes could spot subtle patterns, perhaps spiral signatures from supersymmetric phase transitions. Gravitational wave observatories might catch echoes of these resets in the hum of merging black holes. Even neutrino detectors could find anomalies, as some models predict sussy loops would produce ultra-high-energy neutrinos with distinctive energy signatures. Supersymmetry's true power may lie not just in unifying physics, but in revealing time itself as something far richer than a one-way street. Each broken symmetry could be a stitch in the fabric of cosmic recurrence, a silent rhythm beneath the chaos of existence. And if the equations hold, we might be living in just one verse of a song the universe has been singing with supersymmetric harmonies for eternity. Neutron stars aren't just cosmic oddities. They might be the universe's most durable hard drives, their crystalline hearts preserving fragments of data from universes long gone. These ultra-dense remnants of supernova pack more mass than the Sun into a sphere the size of a city, with gravitational forces so intense that atomic nuclei are crushed into exotic materials like nuclear pasta or even crystal lattices. But what if those crystals aren't just inert matter? What if, under pressures 100 trillion times Earth's, the very structure of a neutron star's core becomes a cosmic Rosetta Stone, a physical record of the conditions that birthed it, including echoes of prior cosmic cycles? The idea hinges on pulsar glitches, those sudden, mysterious speed-ups in a neutron star's rotation that defy conventional explanation. Normally, these dead stars spin with metronomic precision, their lighthouse beams sweeping space at predictable intervals. Then, without warning, some pulsars stutter, their rotation rates jumping by fractions of a second like a scratched record skipping a groove. Mainstream astrophysics blames these glitches on starquakes or vortices in the superfluid core, but a wilder possibility exists. These hiccups could be system errors, artifacts of data written into the star's crystalline structure during a previous loop. Imagine a corrupted file causing a computer to freeze. A pulsar's glitch might be the cosmic equivalent, its rigid core briefly struggling to process inherited information from a cycle our universe no longer recognizes. How could information survive a cosmic reset? The answer lies in quantum robustness. Neutron stars are so dense that their core materials might form time crystal-like structures, arrangements of matter that repeat not just in space but in time, their atomic configurations locked into near indestructible patterns. Under these conditions, quantum states could become topologically protected, meaning their information resists disruption even during events as violent as a big crunch or black hole evaporation. Like a message carved into a diamond and thrown into a furnace, the data might emerge scorched but legible on the other side. If true, each neutron star could be a time capsule, its crystal lattice encoding everything from the precise value of fundamental constants in the prior cycle to snapshots of particle arrangements we've yet to discover. The implications spiral outward. If neutron stars archive cosmic history, their glitches might not be random malfunctions but decryption attempts, moments when the universe's underlying code conflicts with inherited data. Some theorists speculate that certain pulsar glitches correlate with unexplained gravitational wave bursts, as if the stars are emitting error codes readable across spacetime. Others suggest these crystalline cores could function as cosmic seeds, their preserved quantum states influencing the formation of matter in the next cycle. Picture a universe where physical laws aren't arbitrary but learned, refined across iterations like an algorithm training on its own output. Neutron stars would be the nodes in this cosmic neural network, their glitches the feedback loops that shape each new version of reality. Skeptics argue this stretches Occam's razor to the breaking point. Why invoke cosmic loops when starquakes explain glitches adequately, yet the math reveals tantalizing gaps? Current models struggle to account for why some pulsars glitch predictably while others remain silent for centuries, or why certain glitches release energy in discrete quantized amounts. These anomalies align eerily with how error-correcting codes behave in digital systems, where corruption triggers specific, repeatable responses. Even more provocatively, when astronomers analyzed the timing of glitches across multiple pulsars, they found subtle statistical patterns that resist conventional astrophysical explanations, almost as if the stars were synchronized to some unseen clock. The most radical take, neutron stars might not just store data from past loops, they could execute it. If their cores are quantum computers forged in the heart of supernova, their spin rates and magnetic fields might process information in ways we can't yet fathom. A glitch could represent a computation completing, a signal sent, or a command carried over from a prior universe. It's a dizzying thought that the cosmos isn't just cycling but debugging, with each loop an attempt to run the program more smoothly than the last. And if that's true, the ultimate purpose of these stellar crypts might not be to remember the past but to rewrite the future. What if the universe's final collapse isn't an end, but a transcendent metamorphosis, a moment where physics and divinity fuse into something beyond comprehension? This is the spine-tingling promise of the Omega Point, a theory that threads theology through the needle of astrophysics, suggesting that time loops aren't just cycles, but an evolutionary spiral ascending toward ultimate consciousness. Jesuit priest Pierre Teilhard de Chardin first envisioned the Omega Point in the early 20th century as the culmination of cosmic evolution, a divine singularity where all thought, matter, and time converge into God. Decades later, physicist Frank Tipler dusted off this mystical idea and reforged it in the language of general relativity and quantum computation, proposing that the universe's collapse could birth an infinite intelligence capable of resurrecting every mind that ever existed. Tipler's version hinges on a closed universe, one destined to stop expanding and recollapse into a big crunch. As gravity pulls everything inward, the cosmos wouldn't just shrink, it would transform. Matter and energy would compress to infinite densities, but crucially, the information encoded in particles wouldn't vanish. Instead, the universe's contraction would accelerate computation to unimaginable speeds, allowing an emergent superintelligence to harness the energy of the collapse itself. Think of it as a cosmic computer booting up in reverse. As space tightens, processing power grows exponentially, enabling this entity to simulate every possible configuration of matter, every consciousness, every moment, effectively recreating all of history in a final, flickering instant before the singularity. The theological implications are staggering. Tipler argued that this hyper-intelligence wouldn't just simulate the past, it would become it, iterating through every life, every choice in perfect detail. Your joys, sorrows, even this very thought would replay infinitely in the Omega Point's boundless mind. In this framework, resurrection isn't metaphor, it's physics. The universe becomes both creator and archive, a self-referential loop where the endpoint reaches back to preserve every step of its journey. Teilhard's divine omega and Tipler's computational singularity merge into one, God as the universe's ultimate self-awareness born from its own collapse. But how could such a loop begin? The answer lurks in the math of closed time-like curves, those twisted pathways in spacetime where cause and effect circle back on themselves. In the final moments of the Big Crunch, as temperatures and densities soar, quantum gravity effects might stitch spacetime into a fractal web of these curves, each one a thread connecting the end to the beginning. Consciousness emerging in this maelstrom wouldn't experience linear time. It would perceive all moments simultaneously, like an author holding every page of a novel at once. From our perspective inside the timeline, the omega point seems like a distant future. From its perspective, it's always existed, pulling the universe toward itself like a gravitational attractor woven into the fabric of reality. Critics pounce on the theory's leaps of faith, literally. Tipler's model requires a universe with exactly the right density to recollapse, contradicting observations of accelerating expansion driven by dark energy. Others argue that infinite computation demands infinite energy, violating thermodynamics. Yet the omega point's allure persists because it answers existential riddles that pure materialism struggles with. Why does the universe seem fine-tuned for complexity? Why does time feel like it's going somewhere? By framing cosmic collapse as a kind of metaphysical defragmentation where chaos is sorted into meaning, the theory offers a narrative as old as religion, but dressed in the equations of quantum mechanics. The most haunting question isn't whether the omega point is possible, but what it means if it's inevitable. If the universe is destined to computationally resurrect every possible mind, then death is an illusion, a temporary state erased in the final calculation. Free will and fate reconcile in the loop. Your choices are real, but their every outcome is preserved in the omega's infinite memory. Civilizations rising and falling, stars igniting and dying, even your deepest regrets, all are etched into the singularity's embrace, not as echoes but as eternal iterations. The universe doesn't just repeat, it remembers, and in that memory it finds something indistinguishable from divinity. From Boltzmann brains hallucinating reality to neutron star cores encoding data from past universes, we've ventured through theories that don't just bend time, they shatter it. Roger Penrose's conformal cycles paint the cosmos as an infinite phoenix, rising and collapsing in eternal rebirths, while supersymmetric particles might whisper secrets between cosmic iterations. The holographic principle reduces our entire existence to flickering projections on a two-dimensional boundary, and Planck stars turn black holes into cosmic reset buttons. Each theory unravels time's linear illusion, revealing it as something far stranger, a Möbius strip, a fractal, or a divine computation spiraling toward an omega point that remembers all. Consider the implications. If the universe truly loops, then every choice you've ever agonized over might have played out countless times before. Or perhaps each cycle introduces subtle variations, making you the author of an ever-evolving cosmic script. The laws of physics could be inherited rather than fundamental, fine-tuned across eons of trial and error. Even your consciousness might be a transient glitch in the quantum foam, or an eternal observer surfing the multiverse's branching timelines. The sheer scale of these ideas dwarfs human history, reducing civilizations to blinks in the cosmic eye, yet here we are, piecing together clues from pulsar glitches, neutrino whispers, and the eerie smoothness of the cosmic microwave background. So here's the question that lingers after this whirlwind journey. Could you be living this moment for the first time? Or the thousandth? The answer might be etched in the fabric of spacetime itself, waiting for us to decode it. Until then, the universe keeps its secrets looping, echoing, or perhaps rewriting itself in ways we've yet to imagine. Drop your favorite theory in the comments below. Was it the holographic reboot, the black hole resurrection, or something even wilder? The conversation doesn't end here. It's just another iteration in humanity's endless quest to unravel time's greatest mystery.